This is the mega construction site of the largest onshore renewable energy complex in the Western Hemisphere, the $11 billion SunZia Megaproject. To construct this massive infrastructure, the engineering team had to solve mechanical problems at extreme levels. They use explosives to shatter the desert bedrock for foundation casting, operate a crawler crane system with a lifting capacity of up to 1,000 tons to assemble 900 wind turbine units. Simultaneously, they deploy a fleet of heavy-lift helicopters to hoist thousands of tons of steel, facilitating the construction of an 885-kilometer transmission line spanning across steep, rocky cliffs. This video will break down the technical details of transporting oversized, overweight equipment and the actual construction process of the project. Hit the subscribe button to follow in-depth analyses of infrastructure engineering. And now, let's get into the details. The core problem leading to the construction of this megasite stems from a physical and geographical disparity. The state of New Mexico possesses natural wind currents with average speeds among the highest in the United States. However, the project deployment area in Lincoln and Torrance counties is extremely sparse, with a population density of less than 2 people per square kilometer. The total population of this vast area is only about 35,000, resulting in very low local electricity demand. In contrast, nearly 900 kilometers to the west, megacities and large-scale industrial hubs in California, home to nearly 40 million people, have a massive demand for electricity. This region constantly faces the risk of output shortages and localized grid overloads. The reality is that the United States has a massive supply of renewable energy readily available, but completely lacks the infrastructure to transmit that electricity to exactly where it is needed. This imbalance creates a severe national infrastructure bottleneck. To permanently resolve this physical barrier, the SunZia Megaproject was approved, serving as a macro transmission system connecting the surplus production area directly to the key consumption zone. To actualize this macro system, the entire project is divided into 2 independent but synchronously operated sectors. The first component is the production core, SunZia Wind. This is a colossal energy construction site comprising 900 large-scale wind turbines evenly distributed across the New Mexico desert. When operating at full capacity, this mechanical complex can generate 3,500 megawatts of electrical power. However, producing this massive amount of energy is only half the equation. The extreme technical challenge lies in transporting that current across the desert. That is when the second sector, named SunZia Transmission, is deployed. This transmission line stretches a full 885 kilometers, cutting across 3 states, New Mexico, Arizona, and California. It crosses deep valleys, spans the Rio Grande, and climbs steep rocky cliffs. This is not just a standard cable line, but a massive interconnected superstructure designed to withstand maximum mechanical loads against harsh weather, ensuring the 3,500 megawatt current does not suffer energy loss or structural failure during its transcontinental journey. Returning to the first production component, SunZia Wind. The process to bring a turbine tower from blueprints to the actual site is a sequence of heavy mechanical and logistics operations. The first physical difficulty does not lie at the construction site, but on the highway. The turbine components cannot be manufactured as a single block and transported. They must be divided. The turbine tower is divided into 3 to 4 tubular steel sections. The generator assembly, or nacelle, is a space-consuming, dense mechanical block. But the most extreme challenge is the 3 blades, each nearly 100 meters long, made from carbon fiber and fiberglass. To move these record-long components across hundreds of kilometers of road, standard trucks are completely useless. The transport unit must mobilize specialized multi-axle trailers. The wheel axle system of this trailer is capable of independent steering, allowing the entire massive cargo to slide through narrow curves without overturning or colliding with obstacles on both sides of the road. Once the massive components are safely gathered in the New Mexico desert, the next physical barrier immediately appears. How to erect a steel tower over 100 meters tall, carrying hundreds of tons of equipment at the top, in an open area continuously subjected to extreme wind currents? First, the foundation excavation process must face the variation of the desert geology. In areas with standard sand and soil, heavy excavators and bulldozers can directly dig an inverted, bowl-shaped foundation pit, up to 20 meters in diameter and 3 to 4 meters deep. However, in sectors where the geological stratum is solid bedrock, standard machinery is completely neutralized. At this point, engineers are forced to drill holes and use industrial explosives to conduct underground blasting, shattering the natural rock structure. Once the rock core is loosened, the excavators move in to clear and shape the foundation pit. Whether constructed on soil or rock, this expanded design aims to evenly distribute the structural ground pressure across the desert. Immediately after excavation, a thin layer of blinding concrete is spread evenly at the bottom of the pit to isolate the environment, creating a perfectly flat and clean construction surface. Then, a cast steel anchor ring containing hundreds of bolts pointing straight up is hoisted into the center of the pit. Here, engineers use laser surveying equipment to calibrate the leveling of the anchor base with zero tolerance, because even a 1 millimeter deviation at the base will cause the 100-meter tower to tilt off its center of gravity. Once the coordinates are precise, workers proceed to weave tens of tons of reinforcing steel and install hollow conduit pipes for electrical cables right through this ring. Next, dozens of mixer trucks enter the site, continuously pouring 600 cubic meters of fresh concrete to fill the foundation pit. This process must occur continuously without interruption to avoid creating cold joints that would weaken the structure. Once hardened, this 1,000-ton concrete block officially encases the anchor ring, becoming an underground gravity anchor, keeping the tower standing firm against all wind levels. When the concrete foundation reaches 100% load-bearing strength, the high-altitude mechanical assembly process officially begins. The central machine in this phase is a crawler crane system with a lifting capacity of up to 1,000 tons. First, this massive machine is moved into position. Then, the tower erection begins. The crane hoists the first steel tower section, lowering it slowly so the flange holes fit perfectly onto the anchor bolts waiting on the foundation. Engineers immediately use industrial hydraulic wrenches to tighten the nuts with maximum torque. Sequentially, the next tubular sections are hoisted up, stacked, and locked together using high-strength bolts until the tower reaches its peak at over 100 meters high. Next, the crane hooks the cables, hoists the generator assembly, the nacelle, weighing hundreds of tons onto the top of the tower, and proceeds with the mechanical locking. Immediately after, the hub, the hollow core for attaching the blades, is also hoisted and bolted directly to the nacelle's motor shaft. Finally, the rotor blade assembly. Due to the extreme wind resistance created by the 100-meter blades, lifting the fully assembled rotor is physically impossible. The mandatory mechanical solution is single-blade installation. The crane utilizes a hydraulic blade yoke to hoist each blade in an absolutely horizontal position, slowly driving the blade root into the pitch-bearing slot on the hub. Engineers stationed inside the hub immediately use hydraulic torque wrenches to deadlock hundreds of bolts. The internal motor then rotates the hub to systematically receive the remaining blades, completing the entire turbine structure. When the rotor blade of the 900th turbine is locked securely in place, the core production zone is completely sealed. This massive mechanical complex officially awakens, generating a maximum energy output of up to 3,500 megawatts. However, the original current from the turbines is alternating current, or AC. To transmit this immense energy payload across hundreds of kilometers without thermal loss, it must pass through the central converter station to be rectified into direct current, or DC, at a voltage of plus minus 525 kilovolts, exactly as shown in the schematic on your screen. The massive energy payload is ready, but how do we transport it across the harsh desert to the West Coast? As we mentioned at the beginning of the video, this mega project is divided into two independent zones. And now we officially enter Phase 2, the SunZia Transmission Superhighway. This 885-kilometer transmission corridor requires thousands of steel lattice towers crossing two completely opposite geological barriers. In New Mexico, the physical characteristic of dry sand is constant collapse, neutralizing standard excavation methods. Engineers are forced to use an auger drill to excavate the soil, while simultaneously driving a massive steel casing downward to prevent the pit walls from caving in. Once the rebar cage and concrete are pumped to a depth of 30 meters, the steel casing is slowly extracted. At this moment, the wet concrete flows out and grips the rugged earth walls, creating an immense skin friction that deadlocks the foundation deep within the desert. Following this, engineers proceed to assemble thousands of high-voltage transmission towers and string the ultra-high voltage cables. This entire process is executed synchronously along the 885-kilometer route, overcoming every terrain barrier from loose sandy plains to the sheer rocky cliffs of Arizona. Finally, this transmission superhighway strikes directly into the Pinal Central Receiving Station. Here, the massive transformer system will invert the DC current back into alternating current, AC, pumping the massive 3,500 megawatt block of energy directly into the U.S. West Coast power grid. On a macro level, the $11 billion SunZia complex is not just a record in heavy engineering. By combining foundation engineering with HVDC transmission technology, the U.S. has succeeded in relocating the raw power of nature from an uninhabited desert right to the center of consumption, nearly 1,000 kilometers away. SunZia has transcended the boundaries of a mere construction project, officially becoming the standard blueprint for continental-scale renewable energy megaprojects. Our breakdown of the physical limits of this massive site concludes here. Goodbye, and see you on the next megaprojects.